studying about the Gauss law. Let us assume a uniform electric field of strength E along the x-axis. Consider a rectangular surface of area A placed in the uniform electric field such that its axis makes an angle theta with the direction of the field. In other words, the area vector A, which is conventionally taken along the outward normal to the surface, makes an angle theta with the direction of the electric field. The electric flux passing normal to this area is then given as phi is equal to E dot A or phi is equal to EA cos theta. Now, consider a closed surface S placed in the uniform electric field of strength E. Consider three elements, X, Y, and Z, on the closed surface, having areas delta A1, delta A2, and delta A3 respectively. The electric flux through the element X is phi 1 equal to E dot dA1. And since the angle between the direction of the electric field, strength E, and dA1 is acute, the flux phi 1 through the surface is positive. For all such elements, the flux passes from the outside to inside. That is, they have invertly normal flux. Since theta is equal to 90 degrees for element Y, the electric flux for Y is equal to 0. For all such elements, the flux through the surface is 0. Similarly, since theta is obtuse for element Z, the flux through the element is negative. For all such elements, the flux through the surface passes from the inside to the outside. That is, they have an outwardly normal flux. From these observations, we can say that the inwardly normal flux is negative and the outwardly normal flux is positive. Let us now consider a point charge plus Q placed at the center of the sphere of radius r. Let us now look at Gauss' law, which defines the relation between the net electric flux through a closed surface and the charge enclosed by that closed surface. The law is of fundamental importance in the calculation of electric field strengths. The closed surface is referred to as the Gaussian surface. The electric field lines of the point charge plus Q are outwardly normal to the charge, and hence are outwardly normal to the sphere at all points on its surface. The magnitude of the electric field E at a distance r from the point charge is equal to 1 by 4 by epsilon naught Q by r squared. Let us label it as equation 1. So we see that for all points on the sphere of radius r, the magnitude of the electric field strength is the same, and it is directed away from the charge plus Q in an outwardly normal direction at each point. Therefore, we see that at each surface point, the electric field strength E is parallel to the area vector dA, which represents the area of an infinitesimally small elements on the surface. Since E is parallel to vector dA, the electric flux d phi passing through this local element is equal to E dot dA is equal to E dA cos 0, and as cos 0 is equal to 1, d phi is equal to E dA. Let us label it as equation 2. To find the total electric flux phi through the Gaussian surface, we now integrate d phi. Therefore, phi is equal to integral d phi, and this is equal into integral E dA. The total electric flux can also be referred to as the net electric flux. Since E is constant in magnitude for all points on the Gaussian surface, we have integral EdA is equal to E into integral dA. We know that to integrate dA is equal to A, which is the area of the Gaussian surface considered. Now, phi is equal to EA. We know that for a spherical surface, which is the Gaussian surface, in the present discussion, A is equal to 4 pi r square. Therefore, we have phi is equal to E into 4 pi r square. Let us label it as equation 3. Substituting equation 1 in equation 3 and simplifying, we get the net flux phi is equal to Q by epsilon naught. Let us label it as equation 4. We see that the net flux phi is proportional to the charge Q and closed by the Gaussian surface. Or we can say that the net flux is proportional to the charge inside the Gaussian surface. Now, consider two other closed surfaces, S2 and S3, around S1 of any arbitrary shape. We see that since S2 and S3 are closed surfaces, they can also be referred to as Gaussian surfaces. We have seen that the net electric flux phi through S1 is equal to Q by epsilon naught. By definition, electric flux is the number of electric field lines passing normal to a given area. Here, we observe that the number of electric field lines that pass through S1 also passed through S2 and S3, normal to their surfaces. Hence, the net flux through S2 and S3 is equal to net flux through S1. That is, phi is equal to Q by epsilon naught. Here, we observe that the net electric flux phi through any closed surface is independent of the shape of the closed surface. Hence, we conclude that the Gaussian surface can be of any arbitrary shape. Thus, Gauss' law states that the electric flux through any closed surface is proportional to the enclosed electric charge. That is, phi is equal to Qn by epsilon naught, where Qn is in the charge enclosed by the Gaussian surface. Let us label it as equation 5. Now, consider a point charge Q placed outside a closed surface. Here, we see that the number of field lines entering the closed area is equal to the number of field lines leaving it. Therefore, the net electric flux through the closed surface is 0, and it is important to note that the Gaussian surface, which is the closed surface, was not enclosing the point charge. In other words, the net flux through a closed surface not enclosing any charge is 0. Let us consider a cube of side L placed in the uniform electric field of strength E, directed along the x-axis. As the cube is the closed area, and the number of field lines entering the cube is equal to the number of field lines leaving it, from any of its surfaces, the net flux through the cube is 0. Now let's prove the same. For any surface of the cube of area A, which is normal to the electric field of strength E, the electric flux phi passing through it is equal to EA. Now we see the electric flux phi1 through face 1 is equal to minus EA, since it has inward flux. And through face 2, it is phi2, which is equal to plus EA, since the flux is outwardly normal to it. The flux through the faces 3, 4, 5, and 6, that is, phi 3, phi 4, phi 5, and phi 6, respectively, is equal to 0. Since the area of vector E is perpendicular to the direction of electric field with respect to these faces, therefore, the net electric flux through the cube is minus EA plus EA, which is again equal to 0.